Hi guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at the RTX 2080 Founders Edition PCB. So there's not really much else to say. Let's get right into it with identifying all of our major voltage regulators.
Before that, this video is brought to you by us and the limited edition foil graph logo shirt. This 4-color foil shirt uses the iconic GN graph logo with average 1% and 0.1% bar colors. It's printed on a soft, high-quality, and custom-made 100% cotton shirt and is available on store.gamersnexus.net until stock runs out. Once it's gone, we will not be making more of these shirts. We sold out within 2 weeks of our previous limited edition shirt, so click on the link below to pre-order now.
First up, we have, of course, the V-Core VRM, which is the largest and most important because it powers the GPU core, and that obviously uses the bulk of the power on a GPU. Above that, we find the memory VRM, so that's VMEM over here, and that, of course, powers the GDDR6 memory chips. And below that, we had the V-Core right there. Over in this corner of the card, it's basically a corner. We have 3 smaller voltage regulators. These would be for the 1.8 volts. And I'm not actually labeling the specific regulators here because I don't know which one's which. But there will be a 1.8 volts rail, a PEX rail, and a USB-C rail. So the 1.8 volts rail is for a supporting voltage for the GDDR6 memory chips. It also powers NVIDIA's BIOS chips. Those run off of 1.8 volts as well. PEX rail is for the PCIe interface as well as some internal PLLs on the GPU core. And then the USB-C rail is, of course, for the USB-C port on the back of the I/O. Since you can't actually, you need a voltage regulator for that rail. And then over here, we also have what I assume is 5 volts because these power stages run off of 5 volts. So you need power. You need a VRM for the bigger VRM. Funny how that works out. Now then, with all of those, identified, let's get into some of the details of the 2 main ones, which are the V-Core and the memory VRM. So the V-Core here is a 1, 2, 3, 4, 5, 6, 7, 8 phase. And this is actually completely reasonable because we do actually have an 8-phase voltage controller here. And that's actually not that new for high-end NVIDIA cards. I mean, the 1080 Ti already used a UP9511, which was an 8-phase voltage controller. Here we have the successor of the 9511, the 9512, which is also an 8-phase, but adds on a few more features. It goes up to 2 megahertz switching frequency, which is not useful because at that point your VRM's efficiency is going to be terrible. But the idea is that basically if you were using a doubling scheme or a quadrupling scheme, you can run that really, really high switching frequency into your doublers or quadruplers. And on the other end of those, it'll either end up as 1 megahertz or 500 kilohertz, at which point that's actually a reasonable frequency to run into various MOSFETs and power stages. So that's some of the reasoning behind why some voltage controllers can go up to ridiculous switching frequencies when you wouldn't ever want to run anything that high into any of the power stages that are being used with them. So it goes up to 2 megahertz. The other major addition with the UP9512 is that it has an SM bus interface, which previously there was no digital interface whatsoever on the UP9511. That thing, basically the only interface it used, which the UP9512 still uses, was PWM vid, and basically PWM vid is a PWM signal that comes from the GPU core into the voltage controller, and that is used for setting the core voltage. You can't actually ask the UP95, like in the past with the UP9511, it wasn't actually possible to ask the 9511 what voltage it's actually outputting. Like, it was not possible to do that, and so basically your software voltage reading was basically whatever the driver was telling the chip to produce, not what the chip was actually producing, which is just kind of an interesting side note about how the 10 series cards worked. But the 9512 can actually report things like VRM current output, output voltage. You can change the switching frequency. You can change the load line calibration. You can change all of this over the digital, the SM bus that it has. Only issue is, as far as I know, actually writing to it might be disabled by default, and there's no public register maps for the chip. So good luck with accessing that. Though Elmore is there is going to be an Elmore EVC, which is basically a little I2C controller, which actually hooks up to the SM bus on this, and that'll give you those kinds of settings. And the reason why that works is Elmore works at ASUS, so he has access to the NDA data sheets, which include things like register maps. So yeah, there will be ways to actually get control of all those features. It's just not very easy because again, you'll have to solder onto the GPU in order to use an Elmore EVC. Anyways, this does mean that we have a real 8-phase VRM here, and it's not doing any of the weirdness that, say, the 13-phase monstrosity of the 2080 Ti is doing, because I like, that is just odd. That phase count is, literally. But 8 phases is a pretty normal phase count. That's completely reasonable to, get out of a UP9512, because it does actually support this phase count. Now, for the phases themselves, you're looking at just one inductor and one power stage in each phase. And the power stage is NVIDIA's favorite 70 amp smart power stage from Fairchild Semiconductor, the FDMF 3170. So that's 70 amps, and it's a smart power stage. The reason why it's considered a smart power stage and not just a power stage is because it integrates current monitoring and temperature monitoring functionality directly into the chip, and that also includes overcurrent protection and overtemperature protection. The overtemperature protection is not exactly a hard protection, as it basically just raises a flag, but the overcurrent protection will actually just straight up shut the VRM down if you overload it. So it's pretty neat. You can't actually... Well, you'd have a hell of a time trying to burn this VRM out, because it should shut down before you manage to do that. They also have some inbuilt protections for various malfunctions. So in theory, which also the UP95, the new some of the new voltage controllers also have some functionalities that work in hand with that, where basically if one of the phases on the VRM goes down, in theory, the VRM could keep operating as long as the malfunction isn't one of those where basically the 12 volts on this side of the VRM ends up shorting through the power stage to this side of the VRM. At which point you're screwed, because everything on this side of the VRM, which is primarily the GPU core, is going to be very, very dead. Though that is it's not exactly a rare malfunction for a VRM, but it doesn't quite have... Like it's not exactly something you should be particularly concerned about, because it's like VRMs don't tend to malfunction that often. They don't tend to get overloaded that often, especially not when they look like this. But it is a realistic, it is a real failure mode that can occur and does cause major issues, because then you end up with cards where even if you try to repair them, well, this is dead. Anyway, with the FDMF 3170s here, those kinds of scenarios are actually much less likely because of all the built-in protections that they have. Now, the next thing that is kind of interesting, and so the end result of using the FDMF 3170s here is that the VRM here gets a pretty good efficiency, at least within the current ranges where it would normally operate. There are, of course, custom PCB RTX 2080s, which have more powerful VRMs, but the thing is, you won't really notice that difference until you're pushing way more current than an RTX 2080 should ever really need. So let's get into those VRM sort of heat output figures. Now, unfortunately, the FDMF 3170 is entirely spec'd at 1.8 volts. I did scale it down to 1.2 volts using a datasheet for a 60 amp International Rectifier 3575 power stage, just because that's like a nice modern 60 amp power stage that should be relatively good for trying to get should be relatively close to the real world efficiency scaling of this thing, compared to, say, some older power stages, which would have actually had a, worse time handling the higher voltages, because I am pretty sure that these are very much designed for the Intel Skylake Xeons, more so than they are designed for NVIDIA GPUs, even though currently these are especially popular on NVIDIA GPUs, and I've not really seen a bunch of Intel motherboards with these on them yet. let's get into those into those heat output figures. So starting at 200 amps, and also worth noting is the switching frequency in the data sheet is spec'd at 500 kilohertz. They also spec like 750 megahertz, and no, 750 kilohertz, 1 megahertz, and I do believe 1.5 megahertz. So, you know, they do go up to higher frequencies, but realistically, this is going to be running 500 kilohertz. Now, 500 kilohertz switching frequency, 1.8 volts output, you're going to be looking at 200 amps with a heat output of about 23 watts. And at 1.2 volts, you'd be looking at about 18 watts. Now, for comparison, the FTW3 from EVGA with its 12-phase VRM using the exact same power stage would actually be doing about 17 watts at the 1.2 volts rate, at the 1.2 volts output, and about 21 watts at the 1.8 volts output. So very small difference. Like we're talking single digit, you know, improvement in VRM, a single digit lower heat output for the VRM on the FTW3. And that's after it adds a whole extra 4 phases. But the reason for that is rather simple. At low current outputs, the majority of your power loss is not going to be due to the current. It's going to be due to just running the power stages. And, well, you know, basically you can't have, basically the issue is that if, as your current out, like, your VRM's heat output is not going to be 0 when the current output of the VRM is 0. It's going to burn power just to run, even if it's not actually pushing any current. And at low currents, that actually means you're burning a ton of power doing a whole lot of nothing. At higher currents, your primary power loss is going to be just all of the current going through the power stage producing a bunch of heat, and then having a lot more phases actually starts being more useful, which we will soon see. As for 300 amps output, this VRM would produce about 42 watts of heat and about 34 watts scaled down, but a FTW3 at that same output would be producing about 28 watts of heat for 1.2 volts. So you'd be looking at about 6 watt reduction at 1.2 volts in VRM heat output by having the 12 phase instead of this 8 phase. Now going up further, 400 amps output, and we're going to get to where these current ratings go. 400 amps output, you'd be looking at about, reading the long set of notes, 68 watts of heat and about 54 watts of heat at 1.2 volts output. The FTW3, for comparison, would be doing about 40 on that 1.2 volts output. At this point, like, we're talking about a pretty major difference. That's 14 watts, you know, less power consumption. That's probably close to half the amount of power that all of the GDDR6 on this card uses. So yeah, that starts being a significant difference in power consumption right there. And then the highest current rating that the datasheet really makes easy to calculate, because while these are technically 70 amp power stages, they only spec the datasheet up to 60 amps, which is kind of normal. 60 amp power stages normally end their datasheets at 55 amps. And then the lower amp stuff, that actually ends where the current rating ends. But for these 70 amp power stages, they stop at 60. So 480 amps for, 60 times 8. That's just kind of easy to calculate here. So 1.8 volts, you'd be looking at about 96 watts of heat, which is like a lot. And then at 1.2 volts, you'd be looking at about 77 watts of heat. For comparison, the FTW3 would be doing 500 amps because that's a 12 phase. So I actually had an easy time calculating the 500 amp figure and didn't have to go to 480. The 12 phase FTW3 would be doing 500 amps at about 72 watts of heat output for 1.8 volts. And for 1.2 volts, it would have been doing 58. So basically at 500 amps output, the FTW3 VRM would be producing about as much heat as this produces at 400 amps output. Of course, at the reasonable current ranges, like this is realistically, I don't think, like on water cooling, you really shouldn't be able to break that 300 amp figure. So 200 amps is around stock, and somewhere between 200 amps and 300 amps is going to be like your usual overclocking range. So stock to sort of H2O, and I'd say 300 amps, you'd already be sort of starting to look into like dry ice range cooling. So stock, well, I should have also included air cooling because there's obviously custom air coolers and those are pretty good. There. So, you know, really you'd already be pretty much like this VRM is pretty good for everything except maybe LN2. And really, even with the liquid nitrogen, you know, you'd probably not hit that 480 amp figure. You'd still be probably somewhere in the 400 amp range, maybe even lower. 1080 Ti's would actually go into the sort of 400 amp range, and this is technically a bigger die, but it may not scale to as high voltages as a 1080 Ti did. You could push like 1.55 volts into a 1080 Ti, or even 1.6 if you had them really well cooled. With this thing, you're really not gonna like, if this ends up running on less voltage, then, you know, you're not gonna hit that amount of current pull. So even on liquid nitrogen, you'd still not be, you know, in that really uncomfortable 400, like this is a lot of heat. And even this is already a lot of heat, though obviously you'd be somewhere in between these two figures on the liquid nitrogen. But with these, you know, higher heat outputs, it's not like you'd really be limited even on liquid nitrogen with the 8-phase here. You could maybe marginally have a slightly cooler running VRM with the 12-phase on like the FTW3, but practically speaking, you wouldn't really see much of a difference. This VRM shouldn't really stop you even on liquid nitrogen. So yeah, this is a nice PCB. It's a solid VRM. You know, it's not massive overkill. Well, for maybe for stock air cooling and H2O, you could say, yeah, it's pretty overkill for those. But I wouldn't really consider this massive overkill. We get into massive overkill territory when we're talking about, well, say the FTW3, right? That has way too many bloody phases. This is more like reasonable amounts of overkill, or what I would consider a solid VRM, because you do get that really nice efficiency right there at where it would normally run. And then sort of at the 300 amp range, yeah, you could probably do better if you had a couple more phases. But you still wouldn't really notice the difference very much, right? Like, we're still talking single digit reductions in VRM heat output, and that's with going up to a card with a whole extra, you know, 4 phases, which is basically a 50% larger VRM. So, because this is an 8, so going to 12, yeah, that's a 50% increase in phase count, and you'd still not see much of a difference. So this is a really, really solid vCore VRM. It's just not, you know, ridiculously so. And above that, we of course find the memory VRM, which is a 2-phase using yet more of the FD. What on earth is going on? Give me a second. There, fix that. So the 2-phase memory VRM is of course using yet more of the FDMF3170s. So this is massive overkill. The memory VRM, you're looking at sort of current outputs of, say, 20 amps and 40 amps, which is like you shouldn't even hit 40 amps output at all. But 20 amps, you'd be looking at about 2 watts of heat. 40 amps, you'd be looking at about 4 watts of heat. Using the FDMF3170s for the memory is massive overkill. There is absolutely, like, the GDDR6 should never pull so much, like, really should never pull more than much more than 20 amps, because this does have even less memory chips than like a 2080 Ti, because this is on that 256-bit memory bus instead of the 384. So that's kind of the memory VRM, you know, absolutely great, no problems there. The voltage controller is yet another UP9512. Which is kind of an odd decision, because, for example, the 10 series, those would all actually use different voltage controllers for the memory VRM, because that's an 8-phase voltage controller running in 2-phase mode, and that is really kind of silly to do. It's not, you know, like, I get why that, like, it does keep the bill of materials simple, and it may, you know, ultimately it might not cost that much to just keep this chip anyway. But in the past, they would have actually opted for a different chip. Like, they'd have a UP9511, and then they'd have like a UP1666 for the memory VRM. But here they're just like, nah, whatever. Just run the 8-phase chip for the 2-phase memory VRM. So that's kind of an interesting decision there that NVIDIA went for. And then, of course, in typical RTX 20 series fashion, we have 2 current balancing circuits. These don't actually current balance the phases. The current balancing for the phases is, of course, done by this chip right here. That's its job. No, these extra circuits here are for current balancing your oddball 6-pin here, And this is actually just a 6-pin. Like this part of the connector is just like a solid block of plastic. I really don't know why NVIDIA didn't leave that area open. Because if you have one of those, if you have one of those 8 pins that looks like, if you have one of those 8 pins that looks like this, where you have the ones with the separate 8-pin part, like the 2 extra pins separate like that, and they add up like this. Well, you could, on a lot of cards, you could just sort of take this part, and if this wasn't right here, that could just sort of sit, rest there. There's not anything here that it would short circuit out by being there. Short out against by being there. So I really don't get why NVIDIA decided to block that off, because honestly, it just makes, as far as I'm concerned, it just makes cable management potentially a bit more messy, and it doesn't really add anything to the card, right? And initially, I was really confused why on earth they didn't just use a straight up 8-pin, which I still think is just like, why? Why even bother with this? Yeah, I don't know. I don't get what this is supposed to achieve. It doesn't look good. Like nobody's gonna see this once it's plugged in. Nobody, I no idea. Absolutely no idea. I'd honestly argue they could have just kept it as an 8-pin and just made that 8-pin optional, and then just because that's actually supported by the PCIe standard. That's why the extra part of an 8-pin, there's no actual power, no real power transfer. All the extra 2 pins on an 8-pin add is this extra ground connector. They don't actually add an extra power line, right? They add a ground connector and they add a sense line. And it's like they could have, and the whole idea behind that is that extra sense line tells the connector that, hey, you're running in 8-pin mode, not 6-pin mode. So in theory, you can have an 8-pin, which will work as a 6-pin, right? That's why the spec is done the way it is. It's designed so that, yes, you could plug in a 6-pin into an 8-pin. The card can then identify that it doesn't actually have an 8-pin plugged in. It's just on a 6-pin. But then it can decide to run at reduced power limit or something, right? You could do those kinds of things. That's why the freaking sense pins are built in. But no, NVIDIA's just let's just put a block of plastic. I don't know. For such an expensive card, I feel like they could have, used that as an extra feature, but hey, and again, you could also just cram double 8-pins on just about everything with my logic. Because it's well, if you don't need the extra 8-pin, you don't have to plug it in. It's part of the specification that you don't need to do that. But I'd say it's just this is weird. It just looks weird. They should have just used a normal 6-pin. But anyway, they do have these current balancing circuits, and those don't current balance the VRM. No. See, that would be far too useful. No, they current balance the power connectors, because NVIDIA, with this basically power connector system, they'll have a 75 watt power limit on the 6-pin. They'll have 150 watt power limit on the 8-pin, and they'll have another 75 watt power limit on the, well, actually that one on the 12 volt rail, you're only supposed to go to 66 watts. And so because of this, and the fact that NVIDIA actually monitors all 3 current inputs on their cards with, these shunts, you can run into funny situations where, say, you set your power limit on the card to, and I'm just for convenience sake going to set that to 75 watts. I'm too lazy to deal with that. Let's say you set the power limit to 300 watts, right? So the whole card is allowed to pull 300 watts. Well, you can run into a situation where you're going to be pushing, say, on this, right? You're going to be pushing 50 watts into that. And then you're going to be pulling 150 on the 8-pin, and you're going to be pulling 50 on the PCIe slot. And the thing is, yeah, you're not hitting the 300 watt limit, but you are hitting the limit for this power connector right here, so the card starts to throttle, because that's what you want with your card to do. So NVIDIA's solution to this problem that they created, because AMD cards can't actually do this, they don't know where the power comes from. If you wanted to, well, you could do some very odd things to AMD cards in terms of their power systems. There's RX 580s that have a 6-pin that literally isn't detected at all. You don't have to plug it in because it's just in parallel with the existing 8-pin. So that leads to some funny situation. Well, basically it means if you plug in an 8-pin or you plug in an 8-pin and a 6-pin, the card actually doesn't see a difference because the 6-pin's just kind of there. It's not actually properly hooked up. And so those cards don't care where the power comes from. They're just going to grab it and use it. But NVIDIA cards, because of all the lovely power monitoring, they're going to complain if you start overloading one of their power inputs. So you need these power balancing circuits to basically, say this phase, like this would be hooked up to, say, this phase, and this phase is pushing, say, 20 watts, right? And normally this phase would be on that overloaded 8-pin. Well, it decides that, okay, so this is overloaded. So the power balancing circuit reroutes it to the 6-pin, and that frees up the 8-pin, and the 6-pin goes up to 70 watts output instead of just 50, right? And this goes back down to like 130. And then you're back, you've just backed off the power limit and the throttling stops. So that's why NVIDIA has this power balancing circuitry, which I quite frankly feel like, it would have just been easier if you eased up on the power limits. You could have just done that. That would have achieved a similar effect. Though admittedly, some power supplies might not like that a lot, but quite frankly, it's just nobody except, well, there's only 2 companies that make GPUs, so that's kind of hard to argue about. But generally speaking, in the past, even NVIDIA didn't bother with this. So I don't see why they're bothering now. And the things making up the sort of power management system on this card are, of course, the 2 7651Qs, which control the power balancing circuitry. And then for current monitoring, we have these 2 chips right here, which are NCP 45491s, and those are used across all NVIDIA 20 series cards so far, both these and these. So that's how NVIDIA sort of has their power management. Like, those are the chips taking care of the power management. The NCPs monitor the various shunts around the card, like these guys. Also, this right here should be a shunt resistor. That right there should be a shunt resistor. We can also see some little MOSFETs right here, so those would be used for power balancing as well. Then we can have... Where else do we have it? There's more of them around the card. It's kind of hard to keep track of. Like, oh yeah, there's one up here. We have some more random little MOSFETs. So basically NVIDIA adds a whole bunch of circuitry to their cards to better manage the power, the input power, where the power is coming from into them, to reduce the amount of power throttling the cards do because of NVIDIA's very low power limits. So, yeah, but I mean, hey, nice way of solving a problem you created. I mean, instead of just setting the power limit to something reasonable, or just ignoring the fact that you're overloading one of the inputs. It's not like pushing 200 watts through an 8-pin is actually going to cause a problem, because if that did cause a problem, Vegas would be setting people's systems on fire, which they don't do. So also Skylake chips would be doing that. Like Skylake X CPUs would also be doing that, and actually a lot of like past GPUs as well. But yeah, so that is it for the RTX 2080. Solid enough PCB, has the usual 20 series NVIDIA sort of features, 70 amp smart power stages, a whole bunch of current balancing and power monitoring circuitry that, quite frankly, I think is unnecessary. Very solid, you have an extremely overkill memory VRM and a solid vCore VRM to go with it. And yeah, there's not really much else to it. That's it. that's the RTX 2080 Founders Edition PCB. It's solid enough. There's definitely more powerful PCBs out there. I really don't think you'll notice a difference if you actually go to those, though those cards may ship with much higher power limits. And quite frankly, the leading features for RTX 20 series overclocking are basically having a very high power limit, having a really big cooling system, or a good cooling system. Generally speaking, with heat sinks, the bigger it is, the better it is at dissipating heat. So big and good kind of go hand in hand in that sense, but you can also design big things that suck at cooling. That's just but if you know what you're doing, then if you make it just bigger, then generally it'll also be better. If you don't ridiculously screw up the design in the process. So that is it for the video. So thank you for watching. Like, share, subscribe, leave comments, questions, suggestions down in the comment section below. If you'd like to support Gamers Nexus, there's store.gamersnexus.net, where you can pick up things like the Gamers Nexus mod mat, which you can see in the background of the video. And also there's the Gamers Nexus Patreon, if you'd like to, support Gamers Nexus through that. And I run a channel called Actually Hardcore Overclocking, which is why I introduced myself as Buildzoid from Actually Hardcore Overclocking, where I do a whole bunch of other overclocking related content, like more PCB breakdowns, and as well as sort of other stuff that's overclocking related. It's kind of hard to describe. So that is it for the video. Thank you for watching, and goodbye.